Now we come to feature transformation. We still have time, right? 8:52. What is feature transformation? Transformation generally means you are changing the current values to some other value. Let's say I go to the points of each team, and then the points is out of 100. Then I decided to map the values to different scale. And instead of 0 to 100, I need to make them from 0 to 1. Okay, so maybe I go to the value 0, the point 0, I put it 0. Maybe if the maximum value is 100, then I put the value 1. So I'm transferring the values from one scale to another scale, for example. This is, we call it transformation, where you apply new set of values to the existing values you have. Okay, so transformation refers to the process of modifying or transforming the original feature value, and usually for quantitative, in a data set to make them more suitable for analysis or modeling. It involves applying mathematical operations or transformation to the features. Now, feature transformation has different things. Even feature scaling, now we're going to talk about soon, is under feature transformation. Anyway, let's look into them. So either feature transformation where you are looking to apply some mathematical operation like log function, for example here, which help you to handle skewed data set. If you have skewed data, means not normally distributed, and you like to make it normally distributed. Why, Arvin, we need to make it normally distributed? Arvin said, no, you need to do it because some algorithms, they have assumption. In order to work best, they need the data to be normally distributed. Then we follow Arvin's suggestion, and we apply log transformation to our data for those that don't follow normal distribution. Okay, clear? And then we come to scaling. Maybe I tell you generally what scaling is. So scaling, let's say we come to Junlin, and Junlin said, well, I found some features, they have different scales. Total number of bedrooms you have from 1 to 50,000, while the total income or the median income is between 0 and 15. So some values have value between, let's say, 0 to 50K, and some other values, they have value between 0 and 15. So the scale is quite different. And remember the case for your sibling, where he may observe, he might be sensitive in the sense he may think 1,000 cent is greater than 50 ringgit. Why? Because if he look only for the value itself, because he doesn't know about the context, right? So if he look to the value, he may think 1,000 cent is more than 50 ringgit, or 100 cent is more than 50 ringgit. Okay, so in this case, same here. Maybe we have some algorithms, they may think these features are more, they may become dominant because they have more value, but actually their value is not as important as the value of the other feature. Okay, so in this case, what we need to do in order to solve the problem, we apply feature scaling. How about instead of having the scale for the first feature between 0 and 50,000, we make all of them the values between 0 and 1. You see? Sometimes one click work, and some other time I use 10 fingers. Okay, thank you, I should use easier. So we come here and say this is between 0 and 1, and this is 0 and 1. The scale, all of them. Then in this case, we take away the magnitude, like we are taking away the magnitude, the amplifier of the value, the amplified values, and just make them all of them between 0 and 1. Okay? And there are two methods of doing this. There's min-max scalar, and we have standardization. Or they call it, another name for standardization is known as z-score. Yeah, z-score, very good. Normalization. Okay, so we have two methods of changing. I think also I mentioned another one called robust we talk about. So attribute, to remove the dots here. You see now working. I don't know. Anyway, so attribute transformation is a function that maps the entire set values of given attribute to new set of replacement value. So it can be due to changing scale, like the case 50 and K, or maybe changing the distribution. Remember, like log transformation, changing the distribution. So again, to remind you about normal distribution, right, where it follows the bell shape. And suppose if it's perfect, should be symmetrical, 100%. Means if you draw a line to make it two halves, then they should mirror each other. Then back to our data set, if you remember, we had some features that are not normally distributed. They have heavy tail. Then we can apply log transformation. And notice how log transformation has helped, like for example, this one. After you apply, it becomes more normally distributed. Okay? So actually visualization, I can tell you, visualization is quite important. If you like to become good even data analyst, just data analyst, visualization is very important. Like they say, picture can speak 1,000 words, right? So instead of looking record by record, visualization is quite important. So it's advisable in this case to apply transformation to the features before scaling. Also, this is nice tip. When do we apply? Because we have feature scaling and we have transformation. I mean, like, look, let's say I'm interested to apply both. Is it possible to apply both? Yes. I mean these both, what I mean. Yes, it's possible to apply both normalization and scaling. So in case you want to apply both, which one should go first? This one first, followed by scaling second. Okay, so you do log transformation first, followed by scaling second. I think I'll stop here, time's up. But wait, let's see the attendance. Okay, so feature scaling, we stopped at feature transformation. So Arvin might be wondering, what is feature scaling? Feature scaling is part of feature transformation, where you change the values of the current features to new value. Now, this value can be following some rules now we discuss about, but there are a reason behind these changes. It is probably, if you remember when we talked about different scales for some features, like total rooms, total number of rooms, and then we have median income. So the scales is quite different. And some algorithms are sensitive. They may assume that features with larger scale are more important than features with a small scale. Like when you say, oh, the total rooms is 10,000, while the income is 2. So they may assume that total rooms with 10,000 is more important than median income with value of 2. While actually we found during practical that median income is the most important feature with correlation 0.67 or 68, right? So in order to solve this problem, we apply what's called feature scaling. So feature scaling is about when you have different scales. So there's a chance that higher weightage is given to features with higher magnitude, higher value. Scaling ensures all feature contributes equally to the result without losing the shape of distribution. Now, the shape of distribution is going to be same, okay? But the only thing that we are changing is their scales, and we make their scales equal so that the algorithms won't actually be distracted or assume that features with larger value or larger magnitude has more important. Now, I was just checking on you. I didn't see E1. So there are many algorithms or many techniques to apply feature scaling. We have min-max scaler and max ABS scaler. These are under normalization. And for standardization, we have standard scaler and robust scaling. Now, by the way, if you check the internet, you may find that people are using them interchangeably, meaning maybe they call normalization for standardization and standardization, they call it for normalization, okay? It doesn't matter as long as you understand what you're doing. So we have 4 ways we're going to discuss about. The first one is min-max scaling. Min-max scaling, the equation as you see on the right-hand side, Simply you have the old value here, and this is the new value. So as we said, we need to replace the old value with a new value. This is what feature transformation is all about. And feature scaling is an example of feature transformation. So in order to apply min-max scaling, simply we need to find the x-min. What is the minimum value inside the feature? Let's say we're talking about median age. Maybe median age, the minimum value is 1. Then x-min is going to be 1. What is the maximum value? Let's say is 50 years. Okay, then x-max is going to be 50. Then we substitute x for each record we have, and we get the new value. We call it x normalized. This would be the new replacement for the old value for the scale. And x-min usually will give you a value between 0 and 1 if all values are positive. So it's going to give you values between 0 and 1. If you have negative, then the values can be between -1 to +1. And if you notice what we said earlier in feature scaling, without changing the shape or the distribution of the data. So if you see on the left-hand side, the picture, do you have this slide? On your side, you have it. This is the old one. If you want the new one in MS Team. Yeah, I like these pictures every time I keep changing the slides. So notice the shape of the distribution is similar before and after. The only thing is we are changing the scale because pictures speaks 1,000 words. So instead of I talk, then you have a picture you can observe. Okay, so this is x-min scaling. So again, the idea is we rescale the value in range if they are positive between 0 and 1. However, one side effect of min-max scaler is sensitive to outliers. What we mean sensitive to outliers? That means while we are calculating the new values, x normalized, outliers are going to be affecting these values. Anyone can say why? If you check the formula will tell you clearly why it is sensitive to outliers. Why? Why? Again, if you try to understand, you won't forget. If you memorize, definitely you will forget. So look into the equation. Why we are saying that it's sensitive to outliers.
But the value would change.
Yeah, the value would change. But if you check, the equation has some indication that outliers might be affecting the equation. Can you see where? Which part of the equation? So which part of the equation? Where are outliers usually resided?
At the peak.
Yeah, at the peak or at the minimum, right? So look to the equation, we have x-min and x-max. So if we have outliers, let's say taking the maximum value, then outliers is going to be inside the equation all the time, affecting all the new values. So this is why we say it's sensitive to outliers, because outliers may actually affect the calculation, may be introduced and affecting the calculation. So anyway, this is min-max scaling. If you want to use Python, then there's a class called min-max scaler inside preprocessing module. You call fit and transform in order to apply feature scaling. Another scaling called max ABS scaling. Max ABS simply is same as min-max. The only difference is x-min equals 0. X-min equals 0. If you substitute with min-max equation, where x-min equals 0, you will get this equation. Same. X normalized equal x old, the old value, divided by x max, right? So this is max ABS scaling. And the values between -1 and 1 if you have negative. If you have negative value, so they're going to be between -1 to 0 or 0 to 1 if all are positive. Yeah. Sorry, min-max scaler is only positive between 0 and 1. Max ABS scaling, I mix between them. It might be negative if you have negative value. Any example where actually we need to apply max ABS scaling. Any common example where X-min is going to be 0? Okay, but if age equals 0, that means the person doesn't exist, right? Yeah, good example. You see, when you participate, you start to think. So if age is 0, that means the person doesn't exist. But is there any other example where X-min going to be 0? How about pictures? If you take the value of the pixel value is between 0 and 255. So if you are trying to normalize the picture pixels, so just you need to divide by X max, which is 255, the maximum value for a pixel, right? Anyway, if you apply min-max scalar, same result, no difference, because X-min is going to be 0. Then we move to standardization. So now we talked about min-max and max ABS scalar. Standardization, or also called z-score normalization. So it has also another name. Simply, normalization is more radical transformation. The point of normalization is to change your observation. Observation means data point, so that they can be described as normal distribution. So it helps you to change the distribution of the data while maintaining the shape. So the shape, again, of the data is still same if you compare the result before and after. Now, the only difference is the mean value should be 0 when you apply standardization. So the mean would be 0, and standard deviation is 1. And standard deviation is 1. Now, the typical value for when you apply in the equation, so you have mean and standard deviation, the typical value is between -3 plus 3. Okay, but not necessary. They might be lower, like -4, and can be higher, +4. But in case if you got values greater than 3 or minimum than -3, then that means you have outliers. So z-score can be used to identify outliers inside the data set. So if you want to identify outliers inside the data set, you can use standardization or z-score, and then assess each record. Right, Arvin? Then assess each record. If the value lower than -3 or greater than +3, then you have outliers. If you want, you can take out the record away. Okay. Standardization is much less affected by outliers. Still affected, but much less. Where is the affecting part is the mean, because the mean will consider the outlier when you calculate. However, it's still less affected. And it doesn't transform to predefined scale. Unlike min-max, you can define the scale. Say, I want my scale to be 0 and 5. Typically, it's between 0 and 1, but you can define your own scale. Anyway, it's not so important, but just to know. Robust scaling is more actually resistant to outliers. Okay, more resistant to outliers because it doesn't take mean. Unlike z-score normalization takes mean, this one takes median. You don't have it. This is a new slide. Okay, again, you can find the new slide on MS Teams. Okay, so median is less affected to outliers because median, anyway, we know it's less affected by the outliers since you pick the value in the middle. Unlike the mean, you consider each value, all the values inside your data set. So in order to calculate, you take the old value minus the median divided by IQR, which is the interquartile range of feature. Interquartile has a way to calculate simply is the range between Q3 minus Q1. The quartile, or this one, the 25% percentile, this is the 75 percentile. The median is 50%, is the value at the 50%. So this is, we call it the interquartile range of the feature. In order to use Python, just robust scaling, and then you fit and transform your scale. So to understand further, This is an example of visualizing for the interquartile by using what's called box plot. Box plot is simply where you have a box. This is why they call it box. You have a box in the middle, and then we have whisker. We call them whisker. The middle line, this is the median at 50%, 50% percentile, or 50 percentile. This is 25. This is 75. So the box will show you the distribution between Q1 and Q3 according to the median value. And the whisker will show you the maximum, the minimum, and the maximum scale without outliers. The outliers usually will be marked by a circle outside the whisker. This is an indication of outliers. So also box plot can help you to identify outliers as well. Okay? Here is just an example for you. Any question? Easy? So this is IQR. You see this one? This is the distance of IQR. This is the distance of IQR. So as a result, we have these scaling features. For technique, we have standard scaling for z-score. We have robust. As we said, this is more resistant to outliers. So this is one way when you have outliers, it's good to apply. Min-max scalar and max ABS, you may apply when standard deviation is small, so giving you some rule of thumb. But anyway, what you could do, you can apply and see the result of your model is working. The performance is increasing or decreasing. And the distribution, and it's not suitable when you have outliers, as you see, because they are affected by min and max. Usually the outliers will be persisted by min and max value. Again, the idea of applying feature scaling, because some algorithms are sensitive. Remember your sibling is sensitive. He actually looked for the higher value, assuming higher value carry more information or more value, while actually it doesn't matter. So in order to ensure in case if you have sensitive algorithms, then you apply feature scaling. So these are some of the algorithms that are sensitive. Gradient descent based algorithms in general, like linear regression, logistic, neural network, principal component analysis we're going to discuss about later on. Distance based like KNN, K nearest neighbor, K means, support vector machine, and others. In other words, you may keep in mind, especially those, any algorithm that requires to calculate distance, that means the distance is actually subject to the length, how far the data point based on the scale, subject to the scale. Then it's better to apply feature scaling, okay? While these algorithms are not sensitive, they are insensitive to the scale, like decision tree and random forest. So what does that mean? If you apply feature scaling or you don't apply, the result the same, won't be affected, okay? The result won't be affected. As with all transformation, it's important to fit the scalar to the training data only. So you fit, because the scalar, when you apply in Python, there's two functions. There's fit and transform. So which data you need to use to call the function fit? You use the training set. This is using the training set. While for transform, you apply on both training and test set. Okay, so fitting only on the training set. So don't make a mistake while fitting your scalar on the test set. Training set is meant to be used for fitting your transformer.